Now we are going to analyze the analysis of perfect frames by using the method of sections. Okay. In method of sections, as we discussed earlier, among the three equilibrium principles, such as summation of vertical forces equal to 0, summation of horizontal forces equal to 0, summation of moment about any point equal to 0. In method of sections, we are going to use the third principle, that is summation of moment about any point equal to 0. Okay. First here, we have to draw the section lines. Okay, we have to draw the section lines. Like here, first the section line I'm going to draw like this. Okay, that means here the section line 1 1 cuts the member AB and AE like this. Okay, here we can consider, that means the section line cut, that means the truss, into two portions, that is the left side portion and then the right side portion. Here the consideration is any one of the portion you can consider, and then in that considered portion all the point loads which are all acting in the considered portion, that only you have to consider. That means here, for an example, if I consider the left side portion of the section line, I'm going to omit the right side portion of the section line. So here, in this left side, the reaction RA, that only the point load, because the 2 kilonewton, 4 kilonewton, RD, these point loads and all acting outside of the, that means it is not in the considered portion. Okay. So that things and all eliminated. And then even in the considered portion, the whole member, that means here there is no whole member. I will show you in when you are going to discuss the other section line, that time we can see that. Okay. Even in the considered portion, if you have any the whole member which is not cut by the section line, that forces in that particular member you don't want to consider. Okay. The point loads which are all acting other than the considered portion, that we don't want to consider for the calculation. That is only the point loads which are all acting in the considered portion that we have to consider for calculation. And then the members which are all cut by the section line. Okay, that forces in that particular members we have to consider. Okay, this is the consideration. As I mentioned earlier, the section line will separate the portion, that means the entire truss, into two, that means two portion. So here you can consider any one of the portion, preferably the left side portion. Okay, so the left portion of section line 1 1, that I am going to consider. Okay, and then I'm going to take moment about any other points. Like first, I'm going to calculate algebraic sum of the moment about the point E and equate to 0. Here, you can see in this considered portion, there are three forces are there. Okay. That is forces in the member AE, upward reaction force RA, forces in the member AE. Okay. When I'm taking moment about E, whether the force in the member AE, it may act towards the right side or left side, but whatever the line of action of the force AE that passes through the point E. So the moment made by that force will be eliminated. Okay. So only this RA multiplied with the perpendicular distance 3. So RA into 3, that will be in clockwise direction. So RA multiplied with 3. This is in clockwise direction. So this supposed to be counterbalanced by the counterclockwise moment. Okay. Here, this is AB. Here the AB, there are two possibilities are there. If it acts upward, the vertical direction, that means vertical resolved component of the AB that will act upward, then the moment made by that vertical component with respect to E, that also clockwise. Okay. So the possibility is it will act like this. Okay. If this act like this, I just to draw the free body diagram here. Okay. That means this is point A. Here the upward reaction force RA is acting. This one is tension in the member AE. This one is the incline force, tension in the member AB. Here, I am going to consider the moment about the point E. Okay, I'm going to consider the moment about the point E. Here, the same. Here, we can consider the moment about the point B also. Okay. So here, in case if this TAB is acting inwards to the point A, then the vertical resolved component TAB sine 60 that will act downward. The horizontal component, that is the TAB cos 60, that will act, this is the direction, that will act exactly on the same horizontal through point A or point E. Okay. So when I take moment about E, the TAB cos theta, that line passes through the point A. So that will be eliminated. So TAB sine 60 multiplied with the perpendicular distance AE. So we can write TAB sine 60 multiplied with the distance 3. Okay. So here we know the value of reaction or A. Okay. Which is equal to 2.5 kilonewton or D, that is 3.5 kilonewton. This in the reaction calculations already we calculated. So from this we can get the value of tension in the member AB, that equal to 2.887 kilonewton. Okay. And then here you can see for the point A it is acting inward. So for the point B also it is acting inward. So from the direction you can see this is tensile in nature. Okay. So for the same free body diagram, I am going to take moment about the point E and equate to 0. When I take moment about the point B, this one, that is the inclined force AB, that passes through the point B. As per the principle of transmissibility, if the line of action passes through the point B, it is passes through A, it is passes through B also. So moment made by that inclined force will be eliminated. Okay, so only the other two forces we have to consider. Here you can see this or A. This you can consider because this is the line of action of the force or A. So we can consider it is acting anywhere in this line. So if we consider RA is acting along this line, then this will be the perpendicular distance from the point B. Okay, when you consider the moment from the point B, then this will be the perpendicular distance, which is equal to 1.5 meters. Okay, that equal to 1.5 meter. So RA multiplied with 1.5, and here you can see this is acting in clockwise direction. This clockwise moment has to be counterbalanced by this moment, that is the force that is tension in the member AE, and then the vertical distance BF. Actually, this distance as of now is not known, that we have to calculate the value, that means the distance of BF. Okay, that by using trigonometry principle we can calculate. So RA into 1.5. Here from the point A, the tension in the member AE, if it act outwards like this, then with respect to the point B, it will be counterclockwise. If it is inward, that also clockwise, that cannot counterbalance this moment. Okay, so that should act towards outside. Then with respect to the point B, that moment will be in counterclockwise direction. Okay, from the point A, that will be in counterclockwise direction. Okay, so tension in the member AE multiplied with BF. Okay, so here the distance BF we have to calculate. That BF can be considered to be equal to CG also. Here you can see the right angle triangle ABF. Okay, in this right angle triangle ABF or AFB, this right angle triangle AFB, actually this one is a counterclockwise. In this right angle triangle AFB, we know that angle we know, opposite side BF we need. Actually, this is 90 degree. So opposite to this side AB, that will be hypotenuse. So for this angle, BF will be opposite side, AF will be adjacent side. So it's better to use tan 60 degree, that equal to the opposite side BF divided by AF. So from this, we can write BF equal AF tan 60 degree. Okay. So from this, we can calculate the value of BF. Once you substitute BF here, we know the value of RA already. Then we can get the value of TAE. Okay. BF equal AF tan 60 degree. So if you substitute the values, BF equal the value of AF 1.5 tan 60 degree. We will get BF equal 2.6 meters. Then substitute the value of BF here. Then simplify. We will get TAE, that equal to 1.444 kilonewton. Here you can see, as per the direction, from the point A, it is acting outward. So for point B also, it is acting outward. So here, this will be in compression. Okay. This will be in compression. Okay. Then we are going to consider another section line to find out the forces in other members. Okay. Now consider the next section line. That means like this. Okay. This section line cuts the members CD and ED. As we discussed in the previous section line, here you can see this section line separates the frames into two portions. Here, right side portion is the smallest portion, left side portion is the largest one. So here we are going to consider the right side portion of the section line 2-2. Then same principle, the point loads which are all acting on the considered portion that can be taken into account for the calculation. The point loads 2, 4 kilonewtons, this RA, which are all outside the considered portion, that we don't want to consider for the calculation. Okay. Same way, the forces in the members, which are all cut by the section line, that alone we have to taken into account for the calculation. Like the CD is cut by the section line, ED, that is also cut by the section line. Okay. So these two forces in that particular members we have to consider. Okay. So here, the portion which we are going to consider, that is the right side portion of the section line 2-2. Okay. This is the section line 2-2. In this section line, the considered portion, that is right side portion of the section line 2-2. That is a considered portion. Here, first I just draw the free body diagram of this. Here you can see there is one inclined force or inclined force in the member, and one horizontal force in the member. There is a vertical upward force RD. This is point D. This is the force in the member TCD. This is the force in the member TDE or otherwise ED, whatever. Okay. So here, first I'm going to take moment about E. Okay. I'm going to take moment about the point E and equate to that 0. Here you can see the moment, that means the point E, that will be here. Okay. We can take horizontal to this. The point E will be here. Okay. When I take moment about E, here you can see this RD multiplied with this distance. That means this distance we know, that is 3 meters. Okay. Here you can see this ED, that is 3 meters. When you take moment about E, this RD multiplied with this 3 meter, that will act in counterclockwise direction. Okay. RD multiplied with the 3. That will be in counterclockwise direction. So RD multiplied with 3. This is counterclockwise direction moment. That should be counterbalanced by a clockwise moment. Here you can see the TDE. It may act inwards to the D or outwards from the D. Whatever this line of action of this force passes through D and also passes through E. So when we take moment about the point E, the moment due to that force TDE, that will be eliminated. Okay, either this side or this side, line passes through the E. So that moment will be eliminated. So only the thing is this moment. Here the TCD, there are two possibilities are there. If the TCD is acting like this, then we can take this passes through like from point D also. Okay. Then we can take, if it is acting in the fourth quadrant, then TCD sine 60, that will act downward. TCD cos 60, that will act towards left side. If it acts upward, then the vertical, that means away from the point D, the vertical component will be upward. If you have an upward force in D, that will give same direction as the RD. So you will get again on one counterclockwise moment that cannot counterbalance the counterclockwise moment made by the reaction force RD. Okay. So the vertical component of that inclined force, that should be downward. Okay. So this will act inwards to the D. Okay. Then here you can see this vertical component TCD, that will act here. For the difference, I just to draw here. The TCD sine 60 will act downward like this. The TCD cos 60, that will act same line. TCD cos 60. Here you can see this TCD cos 60 again passes through the point E or E, D or E. So the moment, when you take moment about E, the moment made by the TCD cos 60 will be eliminated. Only we have to consider the TCD sine 60 multiplied with the distance 3 meter. Okay, because the TCD sine 60 with respect to this 3 meter, that will be in clockwise direction. Okay, so TCD sine 60 multiplied with 3. This is clockwise moment. So here we know the value of RD. So from this we can get the value of TCD. Okay, that equal to 4.042 kilonewton. And then here the TCD, it is acting inward to the point D. Same way that will be inward to the point C also. So this tend to pull the member CD. So this will be tensile in nature. Okay. Now we calculated the forces in the force in the member CD. Now force in the member ED. For that, I'm going to take moment about C and equate to 0. When I take moment about C and equate to 0, this is point C. Here, this TCD, that is acting exactly through the point D. And as we discussed earlier, this is the line of action of the reaction force RD. So we can consider the RD is acting anywhere, the points anywhere in the line of action. And this distance, that will be same 1.5 meter. So from the point C, when you take moment about the joint C, RD multiplied with 1.5, that will be in counterclockwise direction. RD multiplied with this 1.5, that will be counterclockwise direction. So RD multiplied with 1.5, this is counterclockwise. And this one, here you can see the C, this vertical value, that means this is G, CG, which is numerically equal to BF. The BF value already we calculated, 2.6 meter. Okay. So CG also 2.6 meter, because symmetrically we can see that distance are same. And here we know that here this force TDE, okay, this TDE multiplied with CG, that should balance this counterclockwise moment. Okay. In case the TDE is acting inwards to the D, okay, for an example, if it is inwards, then with respect to the point C, the TDE will act this direction. So the moment made by this one, that also in counterclockwise direction, TDE into the CG, that will act in counterclockwise direction, that cannot balance this counterclockwise moment. So it should be outwards from the point D. Then you can see TDE multiplied with the distance CG, that will be in clockwise direction. So TDE multiplied with the distance CG. Here CG equal to BF, that equal to 2.6 meter. Substitute the value of CG. Then by simplifying, we will get the value of TDE, that equal to 2.021 kilonewton. From the point D, it is acting away from the point D. Same way from point E also, it will act away, outwards. So here you can see this two forces, tensions on the member ED, that tended to push the body. So this TDE, that will be compressive in nature. Okay. So now by using the section line 2, we calculated the forces in the member CD and also ED. Okay. Then 3 forces in that members remaining to be calculated. Okay. That we will calculate. Next, we are going to draw the section line 3, like this. Okay. So here, this section line 3 cuts the members BC, CE, and ED. And then here, this section line separates the frame into 2 portions. Here, the right side portion to the section line is the smallest portion. So that we are going to consider. As I mentioned earlier, the point loads such as RD and 4 kilonewton, which are all acting in the considered portion, that only we have to take into account in the calculation. The 2 kilonewton or A, which are all acting outside the considered portion, that point loads we don't want to consider. Then this section line, in this considered portion, BC member is there, CE member is there, ED and CD. There are 4 members are there. But the section line cuts BC, CE, ED. Only the 3 members. The CD, this member is not cut by the section line. So the force in the member CD, which is not cut by the section line, that we don't want to consider. Okay. So the point loads which are all present in the considered portion, that we have to consider. The forces in the member which are all cut by the section line, that forces we have to consider. The forces in the member which is not cut by the section line, the whole member, that we don't want to consider. Okay. So here, the considered portion, that is the right side portion. Okay. So here, the right side portion of the section line 3, we are going to consider. Okay. I just draw the free body diagram here for our reference. Okay. That means here you can see this is point C. At this point C, 4 kilonewton downward force is acting. This is the force in the member BC, one inclined force. Tension in the member CE. Here another inclined force. Tension in the member CD. Okay. And then here you can see if this is point D, from the point D, there is a horizontal force. Tension in the member TDE. Okay. And at point D, an upward force RD is acting. So TBC, TCE, TDE, RD, and 4. The CD is the whole member. So that we won't consider as the force. CD is the whole member, that we won't consider as the force. Okay. As usual, here we are going to take moment about the point E or point B, like that, to calculate the unknown forces. Here BC, CE, these two are unknown. TDE already we know, that is outwards from the point D, and the value also we calculated. Okay. So here, among these two unknown, to eliminate any one of the unknown, it's better take the moment about the point E. Okay. When I take the moment about E, the tension in the member CE, that will be eliminated. Okay. That means I'm going to take moment about E. Okay. When I take moment about E, this TCE, here actually 5 forces are there. TBC, TCE, TDE, the point load RD and 4 kilonewton. Among these 5 forces, the TCE and TDE, these two lines of action of the forces passes through E. Okay, CE, DE, that two are passes through E. So that two will be eliminated. Okay, moment due to the two forces will be eliminated. So the moment due to TBC, 4 kilonewton RD, these things we are going to consider. And we know that as per the principle of transmissibility, the 4 kilonewton is acting here. So from the point E, that will be 1.5 kilonewton. Okay. So when you take the moment about the point E and equate to 0. Okay. So RD multiplied with 3. Here you can see this is RD multiplied with 3. From the point E, this RD, that is in counterclockwise direction. RD into 3. Okay, RD into 3, that is counterclockwise. Okay, from RD into 3, that will be in counterclockwise direction. Then here the 4 kilonewton is acting here. So 4 into 1.5. 4 into 1.5 from E. That is this side. Okay, 4 into 1.5. This is in clockwise direction. Okay, so this tension in BC, okay, this one, this may act either this direction or this direction, but whatever, this will be at a distance from E, the vertical distance EH. Okay, it may act like this. Okay, it may act like this or like this, whatever the distance. Okay, so here you can see when you take moment about E, here the value of RD, that we know that is 3.5 kilonewton. Okay, 3.5 multiplied with 3. That is the counterclockwise moment. Here we have 4 into 1.5. Okay, this 3 into 3.5, we will get 10.5. But 4 into 1.5, we will get only 6. So here counterclockwise moment is the largest one comparatively than the clockwise. So the moment made by the tension, that means forces in the member BC, that should be in clockwise, then only it can balance the counterclockwise moment, because RD is 3.5. 3.5 into 3, that will be 10. So clockwise moment is more than the counterclockwise moment. Okay. So to balance the extra counterclockwise moment, so this TBC multiplied with the perpendicular distance EH, that should be in clockwise. Okay. Here you can see if this act this direction, okay, then that will be, if this act towards left side, that means outwards from point C, that also in counterclockwise. Okay, so it should act inwards to the point C, then TBC multiplied with this vertical distance, okay, that is EH. Okay, this is the perpendicular distance. So EH multiplied with the TBC. TBC multiplied with EH. Here, we know the value of EH already. This is also clockwise. EH, symmetrically we know that equal to BF or CG. BF or CG, that value equal to 2.6 meter. So substitute the value, the only unknown TBC, that equal to, we can get the value of TBC, that is 1.732 kilonewton. And here you can see for the point C, it is acting inwards to the C. So point B also it is inwards. So the force in the member BC, that will act in tend to pull the body. So this is tensile in nature. Then take moment about B and equate to 0. Okay, actually here you can see the point B, that is extension in H. So here the vertical, that will be F. Okay. Here this FE, that is 1.5. This total distance is 3. Okay. So when I take moment about B, first of all, this RD, okay, we can take this RD that is acting here. I just take here this vertical. This one is 1.5. Okay, this distance is 1.5. From B to C, that will be 3 meters. Actually, the RD that will act here, this will be 1.5. From the point B, that is 3. So it will be RD multiplied with 3. That will act in counterclockwise direction. So RD multiplied with 4.5. We know the value of RD, that is 3.5 kilonewton. Okay. Then this point load, 4 kilonewton. This 4 kilonewton multiplied with 3. This side 1.5, this side 1.5 from the point B. 4 kilonewton multiplied with 3. Okay. This is clockwise. So that have to be added this direction. 3 multiplied with 4. Okay. This is counterclockwise. This one is clockwise. Okay. Then when you take moment about B, the tension in the member BC, that will be eliminated. The tension in the member BC will be eliminated. So RD, moment due to RD, we calculated. 4 kilonewton also we calculated. Then this TDE. This TDE passes through the horizontal point. That means the TDE passes through, we can consider passes through F also. This passes through F also. Okay. So the TDE and the direction we know outward from the point D, the TDE and multiplied with the vertical distance BF. So the TDE multiplied with BF. Okay. That is in clockwise direction. Okay. TDE multiplied with that is the vertical distance BF. So TDE multiplied with BF. We know the value of TDE and then we know the value of BF, the vertical distance, that is 2.6 meter. That is also the clockwise. So if you substitute the value, okay, this clockwise, we have 17.25. This is the moment. But the left side, we got only 15.75. Okay. So here you can see this is greater than the counterclockwise moment. So the moment made by this inclined force TCE with respect to B, that should be counterclockwise direction. Okay. Here, whatever the direction it is going to act, either it may be outwards from C or inwards to the C. Here you can see the horizontal component passes through T, that means B. So the horizontal component or moment made by the horizontal component of TCE, that can be eliminated. Okay. So here the TCE, and then you can see the vertical component is acting downward. Then it will act clockwise with respect to B. So that should be like this. TCE should be like this. Then the resolved component. For understanding, I just put in different color. This will be TCE sine 60 degree. And this will be TCE cos 60 degree. But the TCE cos 60 degree passes through B. Here we are taking moment about B only. So TCE cos 60 degree, that will be eliminated, or moment due to that TCE cos 60 will be eliminated. TCE sin 60 multiplied this distance BC, that is 3 meter. So TCE sin 60 multiplied with the value 3 meter. Okay, that will be in counterclockwise direction. That how to be added here. TCE sin 60 multiplied with 3. Okay, that how to be added this direction. That means with this value plus TCE sin 60 multiplied with 3. So from this, we can get the value of TCE, that equal to 0.577 kilonewton. And here from the diagram, you can see at the point C, if it act inwards, then point E also, it will act inwards. So this will be tensile in nature. Okay. So up to this, we calculated 6, that means forces in 6 members. Okay. So now we are going to calculate the unknown force in the member BE. Okay. The only unknown force, tension in the member BE, that we are going to calculate. For that, now we are considering a section line 4-4. It cuts the portion BC, BE, and then AE also. Okay. So here, as usual, we can consider the left side portion or right side portion. Here, the left side portion is the smallest one. So we are going to take the left side portion. So here, the considered portion, that is the left side portion. Okay, the left side portion is the considered one. So I am going to consider the left side portion of the section line. Four. Then I'm going to take a moment about C and equal to 0. Okay. So first I just draw the free body diagram of the considered portion here. Here, this is point B. At point B, the vertical downward force 2 kilonewton is acting. From the point B, the horizontal force tension in the member TC, and with respect to the point C, we are going to calculate the moment. And then from point A, it's a whole member. It's not a force or cut. That means it's not a cut section. Here, AB is a whole member. From the point A, the force in the member TAE is acting. And then from point B, that unknown force TBE, that is also acting. This TBC, that is acting towards the left side, as we calculated here. Okay, so this TBE, that will meet at the point E. From the point E, this one, that is CG. Okay, so with respect to the point C, we are going to calculate the moment. Okay, so here you can see, and then the RA at point A, RA, an upward force is also acting. Okay, so when you take moment about C, this RA, actually we can consider this RA is acting along this line and it is exactly upward. Okay, and this is the distance which is equal to 1.5 meter. So this RA multiplied with this distance, here 1.5, BC 3. That means 1.5, 1.5, 1.5 up to this. That is 4.5. So RA into 4.5, that will be in clockwise direction. Okay, RA into 4.5. This is clockwise moment. Okay, this will be counterbalanced by, here you can see this 2. That means this is the clockwise moment. This has to be counterbalanced by this 2 kilonewton multiplied with 3 with respect to C. This will be in counterclockwise. 2 into 3. That will be in counterclockwise. Plus, here you can see the BC, the TBC. That line passes through the considered point from where you are going to calculate moment. So moment made by the TBC, that we are not going to consider. TAE, this TAE passes through A, E and also G. Okay, so TAE multiplied with this distance CG. Here you can see this is also in counterclockwise. That means this we have to add this side. TAE multiplied with CG. This is also counterclockwise. We know the value of TAE and then CG. If we multiply this side RA 2.5, so we will get the left hand side 11.25 kilonewton meter. Right side 2 into 3 6 plus these two values. TAE multiplied with the CG, you will get 3.754. So it will be 9.754 you will get at the right side. So here the clockwise moment will be 11.25 kilonewton meter. The counterclockwise moment, addition of these two will be 9.754 kilonewton meter. Here you can see this clockwise moment that is larger than the counterclockwise moment. So the moment made by that unknown force TBE, that should be in counterclockwise direction. Okay, that should be in counterclockwise direction. Here there are two possibilities are there. If it act towards B, then TBE sine 60, that will be upward, then you will get again clockwise. So it should act away from the point B, that is outwards from point B. Then we will split that into two component, that is TBE sine 60. That will passes through the point F. Okay, that means TBE sine 60 passes through the point F. That will be at a distance 3 meters from the point G or point C we can take. Okay, or it is acting at point B. So 3 meter BC. The TBE cos 60, that will act this direction. TBE cos 60. Here you can see the TBE cos 60 passes through the point C. So the line of action of this force passes through C. So moment made by the TBE cos 60, that we are going to eliminate. So only the thing is the TBE sine 60 multiplied by 3. This will be also in counterclockwise, that we are going to add this side. That is TBE sine 60 degree multiplied with this distance 3. Okay, that has to be added this side. Okay, so from this you can calculate the value of TBE, that is 0.577 kilonewton. Okay, so here you can see it is acting this direction. So from point E, that will be this direction. So here you can see this TBE, that is compression in nature. Okay, that is compression in nature. Okay, So guys, so up to this, we calculated the forces in all the members by using both the methods. Actually, guys, this video will come in two parts. Okay, this part 2 solved by using method of section. For this, the reaction calculations and all, you can refer the part 1, which we calculated by using method of joints. Okay, so both the parts you have to see to understand both the method of joints and method of sections. Okay, so finally here I'm going to do the force table. Okay, that is very important thing. Then the force table. Okay, that is whatever the values we calculated, that we have to illustrate it in a table. Serial number, member, magnitude of force in terms of kilonewton, and then its nature, whether it's a tension or compression. First one, the member AB, the force we calculated 2.887 kilonewton, and it is tensile in nature. Second one, the member AE, the force we calculated 1.444, and it is compressive in nature. Okay. The third one, the member CD, that is 4.042. It is also tensile in nature. Okay. After that, the fourth one, that is DE 2.021, that is compressive in nature. Okay, then fifth one, that is the member BE 0.577, that is also compressive in nature. Then sixth one, BC 1.732, that is tensile in nature, that is tension. Seventh one, that is CE 0.577, that is also compressive or compression in nature. Okay. Okay, guys, I hope you all understand. Again, I'm telling this is part 2, that solution for this analysis of truss or frame by using method of section. Part 1, you have to check by using method of joints. Okay. Okay, guys, I hope you all understand this video. Thanks for watching. Don't forget to subscribe my YouTube channel, Vishwaguru, a problem solver, for more number of videos on method of sections, method of joints, etc. Okay. Thank you.